So good morning, everyone. For those joining on the call today for the EMIRI event on fuel cells, we are still going to wait for 1 or 2 minutes before people are joining the call. I see the counter rising up quite fast, so it means that people are quite punctual. So let's wait 1 or 2 minutes and then we will kick it off. So for those who are joining and are still needing a coffee, it's the moment or never to grab something before we start the session. Maybe a little bit of room keeping instructions in the meantime. So today, if you want to ask a question, we recommend that you are using the Q&A button that you can see on the bottom left of your screen. If you would be having any other question like a logistical or you have a problem, you cannot hear us or something goes wrong, of course, feel free to use the chat. But for the questions to the speakers, we would like to channel the questions through the Q&A window because it's much more practical on Zoom. So maybe I can start, Gemma, or wait 1 or 2 more minutes. We have 100+ people registered and we are at 34. So maybe we wait 1 minute more. I will already start sharing my slides. No, just, and this should be full screen. Yeah. So I propose I start with the introduction as people are joining the call. So today we are gathered to speak about materials for fuel cells. For those of you who are joining EMIRI events, we had a session in the past on materials for electrolysis. And then we had another session in the past on materials for hydrogen storage and transport. So today is actually the last session that we are doing on fuel cells. And we will be talking about fuel cells in general. And we will then, of course, be diving into the 3 most, I would say, relevant technologies for EMIRI, which are AEM, solid oxide, and PEM fuel cells. So very briefly, a couple of words on EMIRI, I would say. EMIRI, this is the Energy Materials Industrial Research Initiative. So we try to be the voice of advanced materials innovators, producers, and users in Brussels. That was the European Commission as well as the member states, I would say. And we really try to advocate for the enabling role that advanced materials have in making clean energy and clean mobility technologies a reality. Without materials, basically, our message is that nothing would ever work. So if you do not have a constant innovation in advanced materials, you cannot really improve the technologies, and then you cannot accelerate the transition to a climate neutral society. That's basically the message of EMIRI. We are an industry community coming together, as you can see here on the slide on the right, with some important names in the field of advanced materials industry. But of course, we are supported by a rich number of research and technology organizations, as well as some key associations. So the mantra of EMIRI is really to be as inclusive as possible, and to have the researchers and the industrials work hand in hand, because we need all the brain power needed in Europe if we want to compete in the global arena. When it comes to hydrogen, we have a focus group on hydrogen. We are 83 members active in this focus group. You see some of the names. This is not exhaustive list. It's just a couple of names that are quite active in the groups that we wanted to highlight today. And how do we structure the group? You will see actually 3 names popping up for those of you who are active in that group. It's Karim, who is more looking at production of hydrogen. So he was the one running the previous workshop on electrolysis. Marcel Meus is with us as well. He was looking at storage and transport. And today it's my job to take care of the workshop today on fuel cells. This is a little bit how we distribute the work, but of course this is teamwork. Today, what do we have as a plan for the day? We are having a morning session that is open to everyone, and then an afternoon session which is only open to the members of EMIRI, as well as those who are, of course, speaking this morning. They are invited, of course, to join us in the afternoon session. So in the morning, what we will do is that we will start with an overview of fuel cells market from Stuart Jones from E4Tech. Then we will have a technology update on solid oxide fuel cells from Julie Mougin from CEA. Then we will have industry testimonials from Vincent Meunier from Solvay on materials for fuel cells, different kind of fuel cell technology. So it's always very good to have this information. After the coffee break, a contribution from Michael Dietrich from Hydrogen Europe on how are we funding fuel cells R&D in Europe in the years to come, with, of course, the Clean Hydrogen Partnership in the spotlight. And then a technology update on PEM from Simon Thiel from FC Zurich. And then a technology update on AEM from Emmanuel Vincent from Technalia. And then the wrap-up by Marcel. In the afternoon, what we do is a more, I would say, dynamic session where we are going to review what we have already done on fuel cell technology. And then we will try to discuss on how can we try to set up KPIs on the level of materials when it comes to fuel cells. So that's going to be the purpose of the discussion in the afternoon. But I will talk about this later when we are in the afternoon session. And these slides, actually, I will use them in the afternoon in order not to confuse anyone. So I propose that we kick it off, and it would be from Stuart Jones from E4Tech. So I will give you the floor, Stuart. So feel free to share your slides. I will stop sharing.
Okay. I'm going to try to press on the share screen now. There we go. Share. Okay. Hopefully you can now see my screen.
Yes, it works perfectly.
Wonderful, wonderful. Hi, everyone. I'm sorry I'm new to you all because you seem like a very good bunch of people and I'm interested in what you do because my background is actually in materials, but sadly for me and you, I'm not going to talk anything about materials here, just the market. You'll see it says ERM. Our company's called E4Tech and we're now owned by ERM. And there's a few extra slides at the end where there's some extra bits that I know I can't fit into 10 minutes, and that includes a description of our company ownership. So on to the next slide. This is a summary of the fuel cell industry review that we produce each year. I'm approaching it purely from a market point of view because for you, this is a bit like another chicken and egg. If we have success in the market, then that helps get money and interest in fuel cell development. Equally, if fuel cell development takes place successfully, that only enhances its market prospects. As I said, I'm focusing on the market. We do the review, as I said, each year. This is just from 2021. We're just about to do the 2022 review. We expect that to be complete by April. And this is just an overview of what happened last year, but I've put some things in bold to bring out some key points. The thing I'd like to mention here is that I've chosen my words quite carefully. So things that appear to be quite small often have got quite a big meaning. So 2021 was a good year for fuel cells with 85,000 units shipped, which equates to 2.3 gigawatts of total shipments. And that sounds rather exciting given the past because it's growth. But if we put that in context, wind grew by 93 gigawatts last year, solar by 145, And CATL, a major battery manufacturer, produced a lot of batteries in that year too. The reason I put that in perspective is two things. One is 2.3 gigawatts is actually quite small, though we think it's big. And in addition to that, the fact that wind and solar are growing is only good news, because ultimately, as we know, green hydrogen will result at lower cost. And that is already taking place now, but probably not at the rate that's needed. Of the fuel cells altogether, PEM in transportation took the main share, around 85% of the total capacity. And of the mobility market, Hyundai and Toyota dominate. And the fact that two companies now provide 75% of the overall shipments of fuel cells leads to large volatility in the overall numbers. In other words, if any one of those two dropped out, that rather interesting 2.3 gigawatts would drop accordingly. And even the upscaling that we saw last year on the EMIRI stack peak output, in other words, the number of kilowatts per stack, even that now impacts significantly on my megawatt shipments. Shipments of micro CHP units by number, the largest sector, but relatively small in megawatts. In Japan and Germany, the main markets fell in 2021. But in contrast, shipments of fuel cells for larger CHP and prime power grew slowly to the number shown there. China had a little bit of a slowdown because of policy changes, but we expect that to grow quickly again. Niches such as shipping and aviation are demonstrating growing activity, but only slowly growing. And there are continued investments in capacity by companies, much larger than we've seen up till now. And strategic partnerships are being formed at much greater pace. For example, Hyvia with Plug Power, and so on. There's many of them. Now, what I want to do is to look back at what's happened in the past with fuel cells, what the focus has been. And when we talk about fuel cell markets, we really talk about lots of sub-markets, which are broken down by country and by end use. There's no such thing as a single fuel cell market. But nonetheless, the general focus of fuel cells has been on efficiency, particularly lower energy consumption and lower generating costs and local emissions. And fuel cells have been applied in multiple markets, of which we know mobility is the fastest growing. I've mentioned the two companies championing that, and I've mentioned the potential loss. We also know that there's more interest in long distance trucks, for instance, self-centric, but frankly, the market there is quite limited. It tends to be the US where we've got very, very long, 1,000-mile distances. It's less common in Europe, and therefore battery electric vehicles compete strongly for that market. And there's also a limited market for range extended vans. And that's because CapEx remains a major issue in terms of relative pricing. By far, the largest fuel, if you like, for stationary fuel cells has been natural gas, conceived as a bridge to hydrogen. That's at risk, though, because of the Ukraine crisis. There's been big changes already as a consequence of that you'll be aware of in Europe. And that feeds mostly micro CHP and prime power. There are more stationary fuel cell companies now rolling out new fuel cell models that operate on hydrogen to reflect the fact that economies are seeking to decarbonize. And where we see that fuel cells are successful, this is mainly where strong policy exists, usually in the form of subsidies or tax credits. And it's very fragmented regionally. I'll come on to that in the next slide. And despite falls in CapEx and increasing unit lifetimes, the total cost of ownership, that's the unit itself, everything that goes with it, like warranty and so on, together with the cost of the fuel, is still too high for widespread application. And the most attractive niches have been known for decades: forklifts, emergency response radio towers, remote power generally. And in that, the fuel for those applications is much a part of the problem as the fuel cell itself in cost terms and in logistic terms. There is a niche, for example, for LPG in UAVs, and there are companies that provide product in that area. and that can help somewhat, but clearly not to the extent that we now see UAVs using LPGs everywhere. There are modest markets for camping, championed by Smart Fuel Cell, EFOI, in terms of battery range extenders, in terms of monitoring and logging and lighting towers, intelligent energy. And there's a growing market in hydrogen drones from Doosan Mobility Innovation. And historically, fuel cells rather than hydrogen has been the focus, and with a vicious circle of high costs and low volumes, but this is changing. Now, I said I'd look at the market segmentation next, and I want to show you some instances of how individual countries or regions are growing and how that relates to policy. So if you look at materials handling, that's growing in Europe, and it's growing much more so in North America. And it's largely a function of the Amazon Plug Power partnership. Elsewhere, it hasn't grown nearly as strongly. Cars we know about, I won't dwell upon that. Mostly it's in the form of demonstrations. The specific drivers, for example, particularly in California, where there's political mandates in effect for decarbonisation. Hyundai in Korea responds to the fact that it's an indigenous domestic producer with a very, very strong policy driver in Korea. And that's where most of its units go. In light commercial, I mentioned vans earlier, Hyvia, France, Stellantis, and so on. Trucks slowly growing, buses slowly growing. Lots more emphasis in China, where there's supportive policy and the desire for exports. Ships growing very slowly, aviation growing exceptionally slowly. Micro CHP driven by two national programs, the German KfW program and the NFARM program in Japan. And one of the areas that is growing relatively quickly is fuel cells for prime power, particularly in Korea. And mostly it's again related to policy. And in Korea, it's an industrialized country with wide hydrogen availability. In other words, waste hydrogen from industry, and that helps grow the market. I've just got one more slide to do, and then the rest of the slides I'm going to leave for you as that you can have as a pack, and they explain themselves because the time's very limited.
Thank you.
The rest in terms of what's the future, again, you can read most of this because I know time's precious, but there's been a big shift, as you know, to hydrogen for decarbonisation with over 25 plans in place. More governments are considering plans. Many of the plans are focused on that one individual country perspective. Some of the plans focus on bulk shipping of hydrogen, but the plans haven't yet become integrated, or more importantly, reached the stage of national legislation. And what that means is until they do, the real driver for fuel cells still isn't there. There's a recognition that for fuel cells to be successful, there needs to be a fuel that in itself delivers an overall acceptable total cost of ownership, which is recognized at around about $2 to $5 per kilo of hydrogen. Dependent on the use case, it varies. That's uncompressed, so additional costs like profit need to be added to that, as well as compression and so on. As hydrogen does become more available at lower cost, of course, this will favour fuel cells generally, including stationary systems, but the logistics of hydrogen supply still pertain. It's still a gas, still expensive to compress and to liquefy. There's going to be continued competition with battery electric vehicles. The chicken and egg of volume and costs are still present, but that's, as I mentioned, has moved more now to the hydrogen side. And of course, fuel cells will continue to mature technically in lifetime and performance, and companies continue to invest in the area. Just to show you what is in the rest of the pack, but not talk through it very quickly, so you're aware of it. There's a slide here giving the numbers from FCIR. There's a slide here telling you some of the major investments in capacity by some of the OEMs. There's one here about production capacities relating to mobility, and we see that very briefly, very large production capacities have been set aside for mobility, but the equivalent for stationary is very small, and the story is given in the slide. I've got a forecast here just to 2025. The real point is probably big growth is going to occur beyond that 2030 plus. And then I've just got a characterization of Europe by policy, and for probably the quicker growing market, which is transportation, by the different modes of transportation. So I've tried to keep it really short to facilitate question time and anything else you might wish from me. But if you have any questions, you're very welcome.
Thank you, Stuart. It's like a Christmas gift after Christmas, all these slides that are coming on top. So thank you very much. I think that most of us will then take the time to download and read through. I just want to have one question quickly to you because of the time. But of course, if at the end of the morning we still have some time, we can still take a few more questions. There was a question from Gert Schumacher saying the market share of fuel cells produced by Toyota and Hyundai of 75% is based on PEM and applications in passenger cars, or is it the total market for all applications?
No, it's just PEM for passenger cars.
Only light duty.
They do produce very small unit numbers outside the light duty vehicle segment, but they are so tiny as to be irrelevant. Okay, so Gert, you got your answer. And thank you so much, Stuart. So that's okay, thank you.
Stay with us for as much as you want. And now we'll give the floor to Julie Mougin from CEA. I know that Julie is a bit pressured by time as well, so we will give you the floor right now, Julie, and she will talk about solid oxide fuel cells. So Julie, you have the floor, and thank you for making the time for us.
Thank you, Fabrice, for the introduction. I will try to share my screen. Hopefully it will work. Please tell me if you see my screen full screen or not. Is it full screen now?
Now, yes. Yes, okay. Perfect. Thank you.
So I will indeed give you a brief overview of solid oxide fuel cell, the technology, and most importantly for today's discussion, the current challenges and developments. So if I can. Yes. So I will start by presenting you the technology specificities with the materials and design, and then provide a current status and trends of developments before giving you a flavor of the main challenges and the methodology to address the degradation phenomena. So first of all, for those who are not very familiar with this technology, it is one of the fuel cells, not the only one, but that has the potential to have a very high efficiency, as you can see on the left-hand side. Especially because it operates at high temperature, typically 650–900 degrees. And then we can, due to that, have an electrical efficiency above 50% and up to 60%. And in case we are valorizing the heat, which is also produced, then the total efficiency can go up to more than 90% in combined heat and power. And on top of this, this technology is very versatile because it's also able to operate the way around in electrolysis mode. And if you combine fuel cell and electrolysis mode, you can make what we call a reversible module. And to give you the whole picture, it is also able to co-electrolyze at the same time steam and CO2 to produce the syngas. And then you can address the power to X. It's not the topic of today, but it's just to give you the complete overview. So it's a modular technology, as most of the fuel cells. The core part is the cell composed of one electrolyte and two electrodes. Then several cells are stacked together in order to increase the power. As compared to PEM fuel cell, there is no need for cooling circuits. And then stacks are assembled into modules and consequently modules into fuel cells systems, especially for stationary large power fuel cell systems, as you can see here with the Bloom Energy system for data centers. And finally, it is a flexible technology because you can operate it with different types of fuels, not only hydrogen, but also methane, natural gas, biogas, or syngas, any reformate of hydrocarbons like diesel or kerosene, and also non-carbon fuels like ammonia or AdBlue. It is due to the fact that you can have a direct internal reforming within the anode of the fuel cell, which allows, by the way, the gas management simplification. Of course, provided we have an adequate level of impurities in order to avoid poisoning. For instance, sulfur is a poison for this type of fuel cell. It is a fuel cell that can still operate at different power levels, what we call power modulation, as the other technologies, but it will take longer startup time because you have to heat it up from 20 degrees to 700, let's say, so it will take hours. Not like PEM fuel cell, for instance. So how does it look like? The core part is a ceramic cell. The material are the one which are presented in the bottom. Electrolyte is a heat-rea stabilized zirconia, so-called YSZ. The hydrogen electrode is a cermet made of nickel and YSZ. And the oxygen electrode is generally a perovskite, mainly lanthanum, strontium, cobalt, iron oxide. You can see from this list, there is no noble catalyst. All those materials are electrochemically active at this temperature range. I will not give into detail the different properties that needs to be achieved for the electrolyte and electrodes. You will have the opportunity to look at the table afterwards. And around the cells, we have two other types of components, the interconnects, which are metallic sheets with coatings to some point, and sealings, which are generally a glass ceramic. And then you are stacking this metallic part and the ceramic part in order to make the stack. As far as we come back to the cell and stack design, we can have some planar design, some tubular cells, or also flat tubes, as the one you can find in Japan from Kyocera. And we also have different generations for cells. The most classical one is electrolyte supported cell. It means that the electrolyte is the thickest part with two thinner electrodes on both sides. It is the one that needs to be operated at the highest temperature due to the thick electrolyte, which induces high ohmic losses. That's why there was a second generation which was developed by decreasing the electrolyte thickness to very thin layers, a few micrometers. For that, we need to have another mechanical support for the cell, which is now the anode, the hydrogen electrode. And then you can operate this type of cell below 800 degrees C. And the last one, the most recent one, is what we call metal supported cell. In that case, the mechanic support is not active anymore. It's not the electrode. It's, let's say, a porous metal substrate. And on top of this, you have the three active layers as thin as possible. And with that, the operation temperature is decreased below 650 degrees. It needs to have an optimized microstructure and a stable microstructure due to this very specific porous metal substrates. So maybe to give a brief overview of the current status of the technology, SOFC, the second technology in terms of unit numbers and megawatts since years. In 2021, those figures are from E4Tech. There is nearly 25,000 units equating more than 200 megawatts, which is roughly 60 megawatts more than in 2020. There is clearly a net increase in the shipment by megawatt with large Bloom units for prime power in USA and Korea, and other suppliers like Ceres and Bosch contribute at much lower volume. And in Japan, NFAB shipment has fell in 2021, so the share between SOFC and PEM has been increased in favor of SOFC thanks to their higher efficiency. And there exist other opportunities in maritime sectors, which is expected to grow significantly during the next 6 years. So as far as we are speaking about degradation, I would like to underline here that we now have a good track record with very long-term operation reported in literature. On the left-hand side, it's a short stack tested more than 1,000 hours at Jülich in Germany. And on the right-hand side, is just to say that very often we see some testing reports of more than 10 or 20,000 of hours. What we can say is that the target lifetime is minimum 5 years, And the commercial Japanese systems even guarantee 10 years now and target 15 years with a minimum or no stack replacement. In both cases, the two different results I present here, we see that degradation rate become below 0.5% per 1,000 hours, which is clearly compatible with 5 years of operation. And you can also see a trend to degradation rate decrease over time, which is also a good trend. So here I wanted to show you the target set for stationary solid oxide fuel cell from the Clean Hydrogen Partnership Strategic Research and Innovation Agenda. It confirms the trends that we have to decrease strongly the degradation rate. Right now, it's roughly 0.6, and the target in 2030 is to go below 0.2% per 1,000 hours. In order to reach that, we need to work on what are the main degradation mechanisms. And we can say that all stack components are concerned, the cell itself, but also the interconnect and the glass ceramic sealing, and most importantly, their interactions. We can identify two types of degradation. First, what I could call normal steady state operation. That means the system operates in its nominal conditions, and then you have mechanisms related to high temperature, current density, and overpotential. And on top of this, we can have some degradation induced by transient operation like startup and shutdown, or abnormal operation like failure or emergency shutdown that could induce some thermomechanical loading, for example. So if we try to rank the harmfulness of the identified degradation mechanisms, you can see different aspects, for example, those you can find at the cell level with the nickel agglomeration and depletion, oxygen electrode demixing, but also oxidation of the interconnect, contamination by impurities, or mechanical damaging and cracking. You see a ranking in this table, and of course, we propose to address in priority those which are criticality 1 and 2, and I just would like to highlight in the next slides how we can address them. So we have also to take in mind that for very long operation duration, more than years, we can face an issue that some degradation mechanisms are not visible at short term. You have to wait more than 10,000 hours to see something, especially for the mechanical effects like creep or cracks, or some low kinetics physicochemical mechanisms like diffusion that takes very long time. So it is needed to use different characterization techniques to investigate those mechanisms at the right scale. And in addition, also from the previous slide, we have to keep in mind that degradation is hardly linear or constant. So lifetime prediction by extrapolating short-term tests is easily misleading, even with testing time up to tens of hundreds of thousand hours. So understanding of the degradation phenomena and mechanism at different time domains is mandatory to better predict the lifetime. For that, we can have a quite interesting approach, coupling experimental, advanced characterization, and multi-scale and multi-physics modeling, which is what we do at CEA. And it is useful to be able to link microstructural and material properties and evolution with the reaction mechanisms and the performance and degradation. It is also important to study the degradation mechanisms in a coupled way, because you can have some combined effects. And some teams around the world try to speak about artificial intelligence and computer simulation techniques with machine learnings in order to predict the long-term operation. And finally, we can also try to work on accelerated stress testing, of course, focusing in a way not to change the mechanisms. And to that perspective, electrolysis mode can be seen as an acceleration mean, because degradation is significantly higher in electrolysis as compared to solid oxide, even for the same atmosphere and the same current density. So maybe to give you a very quick overview of two types of mechanisms, we can start with the LSCF oxygen electrode destabilization. It has been reported that we have some strontium accumulation in the bare layer made of gadolinium diphtheria placed between the electrolyte and the electrode. And this amount is much richer in electrolysis mode than in solid oxide, in a fuel cell mode, sorry. And it has been proposed a mechanism with different steps like evaporation and reactivity and release. And this destabilization could explain, for instance, the highest degradation in electrolysis mode as compared to fuel cell mode. And in a similar way, we can also study the nickel agglomeration. So nickel coarsening is found to represent a significant part of the degradation rate. And it was found in the end that roughly it's 30% in fuel cell and 22% in electrolysis. It is not depending on the operating mode, it is only thermally affected. So that is also interesting to see the difference between the two modes. It can really support to understand what degradation mechanism is behind. So to try to conclude, so SOFC is a high potential technology for production of electricity and heat at high efficiency, flexi-fuel, modular and versatile, because you can use it the way around, as I said. The main challenge still remains to improve the durability to reach more than 10 years at nominal performance, even if a strong improvement has been achieved during the last 10 years, I would say. The degradation rate is not really linear or constant, so lifetime prediction by extrapolating is really tricky and even misleading. And we have to understand the degradation phenomena and mechanisms at different time domains to predict the lifetime. I hope I convinced you about the power of an approach combining experimental, advanced characterization and multi-scale and multi-physics modeling to first understand the reaction mechanisms and make the link between materials, microstructure and properties. It will be very useful to propose microstructure optimization and or new materials to improve the performance, but also to deeply characterize the degradation upon operating conditions to understand those mechanisms in order to propose microstructure optimization and new materials to improve the durability. Accelerated stress testing will also be very useful. Electrolysis can be found as an acceleration. And all in all, everything should lead to the development of an SOFC technology with better performance and durability, meeting the targets set, for instance, by the European Commission. So that's the end. Thank you for your attention.
Thank you so much, Julie. I think it was a very rich presentation, very nice overview of all the degradation mechanisms. So I have only one question that is now from Michael from Hydrogen Europe. So he's talking about the recycling of solid oxide technology. Where do you see the challenge? And for example, do we know how to retrieve this strontium, which is, if I remember well, quite a scarce element as well?
Yeah, that's a big question. So far, I would say that solid oxide fuel cell or solid oxide electrolysis is not so much recycled so far. If you look at the stack technology, you have the ceramic part and you have the metallic part. And what is quite easy to recycle is the metallic part. And it is interesting because the metallic part accounts for the major part in terms of weight in the stack. For that, you can simply put it in an electric furnace to produce steel, for example. For the ceramic parts, it's a little bit more tricky because the different layers of the cell are really strongly imbricated with sintering. So you have to separate, the amount is very small. So, of course, some techniques exist, and we could adapt to this technology methods that exist for batteries or whatever. But so far, what I understood from manufacturers is that it's too expensive as compared to to the use of new materials, but you're perfectly right. Some of those components are critical raw materials, and in the future, we might take care about this, and I hope we will have opportunities for projects, especially funding by EU, in order to evaluate techniques more relevant and with a better yield to recycle and recover some minor elements in this technology.
Thank you so much, Julie. I think in general, it's true that the circular economy elements of the hydrogen technologies is still not yet as developed as for batteries, and it's going to be a major theme of the work in the years ahead, be it for PEM or solid oxide or other technologies. Absolutely. So thank you so much, Julie. I know that you are pressed by time, so thank you so much for making the time.
Thank you.
And thank you. Have a nice day. And I will now give the floor to Vincent Meunier from Solvay. He's the Sales and Development Director for the Green Hydrogen Platform at Solvay. So Vincent, you have the floor. I hope that you can share your slide.
Absolutely. Well,
we can see it. Yeah.
You for the invitation, and thank you to all of you to attend the session. Just let me know if you see the screen, because I don't see you anymore.
Yes, c'est parfait.
It's okay?
Oui.
Perfect. Really good. Well, thank you. I'd like to present you the contribution that Solvay intends to make to the hydrogen applications. And there will be a focus here on specialty polymers. But there are also some other materials that we are working on that will be mentioned in the presentation. I'll have a few slides on the Solvay group, going fast through that, and then specifically exploring the use of fluoro materials and polymers to try to address what has been said before by Stuart Jones, which is the viscous circle of high cost and low volume. I think we have some solutions for this. Solvay, as you know, it's a large chemical company. We represent about 10 billion in sales, and we are clearly focusing on innovation as well as sustainability value for all. And this is, I think, a key message that really rings a bell with the EMIRI value. We have the Solvay One Planet goals that you see here about climate, about resources and better life. How do we address that with specific targets? And what are the progresses done over the last 3 years? You see all that in the table, and I will not spend too much time on this, but I think it's important you see that all this is well defined, well quantified, and we're making really strong progress, for the planet. And what does it mean also in really simple terms about, carbon neutrality? The groups want to be carbon neutral by 2040 for everything except soda ash production. And once we include the soda ash in the perimeter of this, then we have to push the date by 10 years to reach 2050, where we intend to be totally carbon neutral, with an associated investment of 1 billion to make it happen. And this is really, I think, a major initiative that drives also all the R&D and investments that we do today. I've heard this morning some comments about, the fuel cells, the materials, and we just had some information about the solid oxides, and there will be some presentation on PEM and AEM in the future later on today. We Solvay have a lot of options, but how do we make sure that those, let's say, options are known to the market? Well, we do that through the platforms. So we create, let's say, limited teams that are the focus for requests coming from the market, and for, let's say, also having dedicated expertise to work on the development of programs and researchers. So those are the 4 platforms we have, with batteries, thermoplastic composites, the green hydrogen platform that's for us today, and the renewable material and biotechnology. So we got a big company, but those are the, let's say, the way we operate. We give to the marketplace a really limited number of interfaces, and then those interfaces will go internally to find the solutions for the needs of the market. We intend to grow, let's say, the turnover of Solvay by 10 billion through those platforms. So it's a substantial effort. I will skip this. I will just let you know what we do here. So earlier today, we heard that there's been presentation on the production of hydrogen, on the infrastructure, and on the end users, the fuel cell today. We, as Solvay, consider that the redox flow battery should be part of the solution for the H2 revolution, which means the storage of the electricity. And this is usually done with a redox flow battery when it's done at scale. And this is where the ionomers are being used. So the fluorinated ionomers, as well as potentially other functionalized, let's say, aromatic materials, are the key elements for the redox flow batteries. For the electrolyzers, I will go into details there, but you will see that clearly polymers have a major role to play in this field to reduce the cost, to increase the performances, and to really increase the flexibility that we can expect from the electrolyzers. For the infrastructure, we have all the composite materials that could be used for the H2 tanks, and Solvay has also large capacity to store the hydrogen in the salt mines, and this is a substantial, let's say, quantity of product we can store. And then for the fuel cells, this is where you have a lot of additional materials that we go through in a minute. So this is exactly what I wanted to spend time on. If you look at the fuel cell, and we take the example of a car here, but it could be a truck, it could be a train or a boat, we split the system in two big subcomponents. The fuel cell itself, the engine block, if you could say it, and then the hydrogen pressure vessels. So we have expertise and we've had expertise for the fluorinated ionomers for more than 20 years, 25 years in fact, making the perfluorinated sulfonyl acid material called Aquivion. And there we synthesize the product for producing the electrodes, the binder of the electrodes, but as well for making the membranes. And the membranes are usually done through a coating process. And this is where the expertise of the polymer, is key. We can play there on the mechanical properties of the material. We can play on the functionality, so the conductivity, if you wish, of the membrane. Then we can also work on the, let's say, coating characteristics of those solutions. And for that, we will supply powder or dispersions according to the needs of the membrane producers. In the membrane field, you see different actors doing different things. Some are making the polymers and the membranes and commercializing both. Solvay has decided to produce the polymer and let the membrane producers of the world develop their own membrane for their customers. If now we go next to the membrane and we look at what keeps everything together, we're looking at the sealing materials. This is the source of major issues and leaks. And for that, we have, let's say, a pretty long experience in hot water management, in the plumbing application. And this is where we draw the aging behavior of our materials into the definition of new gaskets products.
Vincent, 2 more minutes?
Yes, okay. So a lot for gasket products. And then for the balance of plant, this is where you have also all the materials that are used at scale that can be injected instead of being machined. What you have to know is that we have the well-established supply chains, we have the competencies, but the fuel cell industry doesn't know it yet. So we have to educate them, and that's what we are doing. This is for the electrolyzers. You have also some products, and we are making also ion exchange membrane development. This is a point that I think is important for all of us, on top of the PEM. And we are really active in the diaphragms as well, and solid oxide, as you might know. Those are all the specialty polymers, let's say typical properties, but in fuel cells, all those things are valuable. And we can really bring that together with the existing product portfolio or develop it for the application. Key takeaway about the polymers. Strength is that those materials are enabler to simplify the fuel cell and the electrochemical systems. Function integration, weight reduction, speed, no waste, recyclability. We have the technological background to simulate, design, process, and improve the performance of those materials and do the material formulation that is needed. And we have all those well-established labs to do that. The points of attention that I'd like to raise. Specialty polymers, it's a scarce resource. It's a dimension for existing application. The fuel cells and electrolyzers will use huge amounts of that. This could be, let's say, inducing some allocation and tension. We also need, for future investments to meet the needs, a predictable regulatory context. This is key for not only the fluorinated polymers, but everything that we make. And what I would like to say is that we are there to be working with the actors in the field to make it cheaper, more affordable, using the automotive expertise that we have in making everything at scale. That's really, in a short, let's say, moment, the different things that Solvay can bring to the table for the fuel cells. Thank you, Fabrice.
Thank you, Vincent. Yeah, it was a very rich presentation as well. I'm convinced that the Solvay product portfolio will tackle hydrogen in the future. That's for sure, with everything that we have seen. I just had one question. I read about 3M announcing before Christmas that they would exit the manufacturing of perfluoroalkyl substances. So,
absolutely.
So I do not know if you can react about that and tell us a little bit what it means for the PEM technology, for example.
Absolutely. So the specialty polymers, it's a world of, let's say, highly concentrated number of players. And that's something that we need to know. So they usually are 5, 6, 7 players active in a given chemistry. We developed, let's say, the chemistry to have a sustainable industrial process so that we will have the product available for the long term and according to the regulatory context that we are given. And this is what we do to secure the production of our, let's say, fluorinated materials. I cannot comment on what the other actors are doing, but we acknowledge the fact that through their communication, there will be more requests coming our way, more requests for the ionomers, more requested for the other products. And we are there, let's say, to take the challenge of looking at the requirements of the customers and see how we can provide alternatives to what is being, let's say, taken out of the marketplace.
Okay.
But we cannot comment on the other one's approach.
I think that in the months to come, we will have to look at what is the regulatory impact of such a company announcement, because it may, of course, maybe confirm some of the policymakers in their assessment that we challenge maybe. But of course, I think that it will have an impact that we will have to monitor.
Yeah. If I may say, Fabrice, one additional element is that the fluorinated polymer, it's one for the ionomers, to make ionomers. We are developing also a lot of, let's say, research targeting maybe some aromatic ionomer materials,
yes,
non-fluorinated ones, so that we have the chance to have a really strong position in aromatic materials.
Yeah. Okay. So the appetite for substitution may be impacted by that. Okay. Thank you so much, Vincent.
You're welcome.
I propose that we still allow you to have all a small coffee break if you need it. And I would recommend that we start at 11:30, so in 6 minutes, and we will start then with Michael from Hydrogen Europe on funding possibilities. So have a quick grab of a coffee or a tea, and we will see you in 6 minutes. So hello again, everyone. We are back from the very short coffee break. I hope that you had time to get the needed caffeine. And now I'm going to give the floor to Michael Dietrich from Hydrogen Europe. I hope, Michael, you are also with us, and I will give you the floor. So feel free to share your slides.
Merci, Fabrice. Thank you very much. Good morning, everyone. Thank you very much for this invitation. I'm glad to present today an overview of Hydrogen Europe and the Clean Hydrogen Partnership. I will start sharing my screen. And you should be able to see it. If someone can just confirm that you can see my screen.
Yes, perfect.
Okay, thank you. Off we go then. Moving to the next slide. Yes, okay. So let's start with the beginning. Hydrogen Europe, who we are. So we are a trade association representing the interest of the hydrogen sector in Europe. You can see on this slide the structure of the organization. That is quite a classical structure. Just to say, in January 2018, we were 7 staff. I was the 7th one to be recruited. And today, 5 years down the line, we are almost 50 staff. So quite a substantial growth. And today, I'm glad to see that one of my colleagues, Priscilla de Carvalho, is online and following this webinar. She's a key person for anything that is related to materials, recycling, CRMs, etc., etc. And myself, Michael, I'm part of the techno and market department together with Priscilla, but within innovation. The Clean Hydrogen Partnership, who was previously called FCH2GU and previously FCHGU. What is it? The general structure, it's a PPP, public-private partnership, with on the private side, Hydrogen Europe, together with Hydrogen Europe Research. And we have a contribution in kind of 1 billion euro to the Clean Hydrogen Partnership. And on the public side, we partner with the European Commission, the DG RTD, together with DG NR and DG Move, and their contribution is 1 billion in cash to the Clean Hydrogen Partnership. So altogether, we have a total budget of 2 billion euro minimum, this to facilitate the transition to a greener EU society through the development of hydrogen technologies. We often refer to the partnership. We also refer to joint undertaking. That is a specific type of partnership, but we don't need to enter into the details of this today. We do not come from nowhere. We have a strong legacy. We have 15 years of R&D experience through the fuel cell and hydrogen joint undertakings. We were organized in several pillars. One pillar was energy, where fuel cells for power and CHP was addressed. The pillar mobility, where fuel cells is very present, together with cross-cutting and overarching activities. You have an overview on the right-hand side of the spending of budget from those two previous partnerships. About 300 projects supported for a bit more than 1 billion euro of investment from the EU, and a substantial share of this was allocated to fuel cells, and we will continue within the Clean Hydrogen Partnership. It's not because the words fuel cells have disappeared from the name of the PPP that we do not address it. Far from this. Very briefly, I wanted to show the funding that was allocated to end users. So I'm not talking particularly on fuel cells here. It's a little bit broader, and fuel cells are encapsulated into those values. So you can see on the left-hand side, the funding for the pillar 3, which is related to transport application from 2008 to the present. And on the right-hand side, the pillar 4, that is heat and power, same timeline, 2008 to present. I did not make the total sum of those numbers because I lacked a little bit of time, but I warmly recommend that you use the link that I indicated in this presentation and have a view at the program review report of the Clean Hydrogen JU. It's very, very instructive. Coming to the Clean Hydrogen Partnership, we have general and specific objectives, which for the sake of time, I will skip and leave it to your reading since it's quite a generic element. I'd rather spend time on the structure that we have to address R&D needs within the hydrogen sector. So we are organized across around the 3 main pillars. First one being production of hydrogen, then distribution of hydrogen and end uses of hydrogen. Under the pillar production, one of our flagship roadmap, so you can see RM standing for roadmap, is of course electrolysis, but we do not do only electrolysis, we also cover other modes of production. For the sake of clarity, blue hydrogen is out of our scope, but we can easily work on technologies that will use bio input, for example, or a direct split of water from solar energy, that type of thing. I will not detail the distribution, it's quite straightforward, but still, we cover large-scale storage all the way to distribution of hydrogen via refueling stations. For Technical Committee 3, which is about mobility, here it's quite important for this group today because that's where we have the roadmap 10 that develops a building block. So power and energy systems, so fuel cells and tanks. And this roadmap will serve all the roadmaps that are below. I will introduce it in the next slide. And same goes with heat and power application, where we have a dedicated roadmap, roadmap 15, on stationary fuel cells. And then we have cross-cutting and overarching activities addressing LCA, sustainability and recycling, but also public awareness, education, RCS, safety, and so on, together with supply chain issues, which is relevant again to this group. How do we ensure that we can have all the production means in place, bearing in mind the need for materials that we have? And we develop as well hydrogen valleys. So here it's about implementation of ecosystems, combining both production, distribution, and end uses together. So we do all of this within the partnership, and we cover TRLs, technology readiness level, from 2 to 8. In other terms, we are very broad, and we cover a whole ecosystem. So 2 billion euro is a very nice figure, but when you divide it per 7 and per the number of roadmaps, we need to make very good use of the money, and we need to develop synergies with other initiatives, of course. A quick focus on the roadmaps of interest for this group, roadmap 10, building blocks, and roadmap 15, stationary fuel cell. So as I said, the roadmap 10 on building blocks will serve all the applications that are within the same group. So roadmap 11, application on road, so trucks. Roadmap 12 for anything that is floating, so ships and boats. Roadmap 13 for aviation, and roadmap 14 for rail application. So whenever we can apply those building blocks across those applications, that's good. But in some cases, especially for maritime and aviation, we may develop specific building blocks dedicated to those sectors because that's very, very specific. We have synergies and spillovers with the roadmap 15 that is about stationary fuel cells, and we cover all type of technologies for industrial and residential applications. So we have synergies between TC3, Technical Committee 3 with the roadmap 10, and TC4 with the roadmap 15. For example, we can explore in terms of balance of plant, what can be standardized for those applications. Main type of technologies covered, PEM and solid oxide, but we also cover other emerging technologies, AEM one of them, of course. As I said, TRL coverage is very broad, from TRL 2 all the way to TRL 8. And within the Clean Hydrogen Partnership, we focus on larger systems, mainly for heavy-duty applications. We do not stop here. Within the valleys, we also do integration of those systems into their hydrogen ecosystem and more broadly energy ecosystems. This is a short overview, and you have the link to another very interesting document that was mentioned by Julie Mougin from CEA when presenting the solid oxide technologies. We have the SRIA, Strategic Research and Innovation Agenda of the Partnership, where you can have a view on the list of which actions we intend to take to further progress the technology. Back to the PPP. Overall, budget distribution, approximately, you have on the right-hand side the repartition per TRL. So you can see a small share to early stage actions of 10%, about a quarter for development action TRL 3 to 6, a more important share for demonstrations because they are CapEx intensive, of course, and then 1/4 for development of ecosystems. And the funding rate is is the same as Horizon Europe because that's a PPP under Horizon Europe. So research and innovation action up to 100% funding rate, innovation action up to 70%, and the CSAs up to 100%. Something very classic. We are not the only ones addressing hydrogen. There are several other PPPs and other instruments addressing hydrogen, and we need to be very good in the development of synergies. So we have several ways to develop synergies. We can first of all use our members, our common members. Some of the attendees today are part of Hydrogen Europe or Hydrogen Europe Research, for example. So a link can be made using those members. At association level, Hydrogen Europe is discussing with EMIRI, and we could further reinforce those links and exchanges. And then at the JU level, we have our program office that discusses as well with EC services for other PPPs that you can see on the right-hand side, and I will comment shortly after. Then at commission level, there is an inter-partnership assembly. And within our governing board of the JU, we have what we call the stakeholder group. And I'm glad that EMIRI is part of the stakeholder group, so can provide feedback when we develop topics for our annual work plan. The consultation between PPPs should become systematic with feedback on topics under development on both sides and development of common roadmaps based on strategic research and innovation agendas with common objectives so that we can ensure a smooth development across the whole value chain. You can claim that we will produce 20 million tons of hydrogen by 2030, but it will be impossible to do it if we do not take into account at the very beginning the need for materials that was indicated earlier, for example. The general concept is that the Clean Hydrogen JU develops the technology bricks and other PPPs will integrate them. In reality, other PPPs, they have hydrogen in scope, but that's not all of their duties. They have other technologies to cover. And this is why we also have the possibility within the JU to demonstrate those building blocks and do a bit of integration. On the right-hand side, you can see all the PPPs that we are cooperating with. And here it might be good actually to add EMIRI on the picture. Should the opportunity arise, I think we would be welcoming this. I'm still talking about this. So we have several members in common, and the working group of what you guys are doing is of high value to Hydrogen Europe and Hydrogen Europe Research. And I think there is potential to better integrate outputs of your work into our work. And we need to ensure that this work is fully considered, but I wouldn't develop a prescription effect either. But it would be good to have a better alignment on our respective activity. As I mentioned, EMIRI is already part of our stakeholder group, so that's really good. And we are all very aware that time is the essence, so we should avoid duplicating efforts at all costs. And our positions, respective positions in supply chains are quite complementary, and we can refer to the example of the 20 million tons. If we don't take into account materials, there will be an issue. So in my humble opinion, I think there is a good potential for cooperation. Once again, I thank EMIRI for the invitation. And I think on this, I'm done with my presentation. I hope, Fabrice, that I did not go beyond the time allocated and we have a little bit of time for questions. Thank you very much.
Thank you so much, Michael. Actually, the timing is perfect.
Yeah, there you
we
go.
are back to the initial timing. So thank you so much for that. And also thank you for the supporting words. I agree with you that the application is, we don't have time for that. So we need to better integrate what comes out of EMIRI into the thinking process that you have at the level of the partnership. And this is what we plan to do with the technology sheets that we will be talking about in the afternoon. I do not see questions in the Q&A, but I had a question about, since you have this kind of broad view about international comparison between Europe and obviously Japan and South Korea on one side, and on the other side, the US. How do you see the position of Europe in innovation on hydrogen technologies? Are we still maintaining leadership, or are we losing slowly the pace?
No, I think we're quite good, and we were precursors in the past in developing those technologies. Now we need to have the right policies in place to keep this pace, because other parts of the world are going fast, very fast, and catching up actually. If you look at the case of electrolysis, for example, the cost per kilowatt is relatively low elsewhere than in Europe. So we really need to accelerate and bring down the cost. And just to speak about this, and I think it's really good because it stimulates a little bit Europe in this competition, and it shows the need to urge in terms of policies. Then for innovation and R&D, the PPP is here, but there is also other instrument as I presented. So there is funding available, and there is funding available for R&D, but not only, also further down the line for a large-scale rollout. I can think of the ETS Innovation Fund, for example, or even the IPCEI's format. So there are some possibilities, but again, time is the essence, and even though we still have possibly an advantage, others are running very, very fast.
Yeah, I think that competition is good if it's fair, and if it helps to innovate more. Actually, it's not a bad thing. Maybe also a small comment about what we discussed, the move away from fluorinated compounds in the industry. Is this something on which you can comment as well?
Yes, so we're exploring it. There were, I think, projects in the past addressing this topic. If substitution materials could be developed at the same cost, same level of performance, same durability, same etc., this would be good. Now we need to compare a little bit the drawbacks of fluorinated products versus advantages they will bring, and especially with the challenges we have with our energy system. And if those products are well encapsulated into all technologies, I don't think you can exactly compare it with the pan that you use daily in your kitchen or your jacket when you go outside on a harsh weather. So it would be good to be able to use still those materials within our technologies. Meantime, we are working on the development of substitutes, and I think there are calls dedicated to this within Annual Work Plan 2023 that has just been published, and maybe more opportunities will arise in the future.
Okay, thank you so much, Michael. Maybe I can conclude your part on saying that the call for Clean Hydrogen Partnership has been published, I think, 2 days ago or 3 days ago, recently. So everyone should now Google it and have a look at the funding which is made available for the course to come. And if there are questions, I guess they can go back to you.
Yes, and I will post the links to the call and to the info day that will happen on the 26th on the chat.
Okay, thank you
very
so much, Michael.
Thanks.
So now we are going into a technology update. We had the SOFC previously, and now we are going to explore, I would say, PEM technology with Professor Dr. Simon Thiel from FC Jülich, Vincent for the last technology update of the morning, which is about AEM. So Emmanuel, we can
Yes.
see you, and we let you share your slides.
Okay.
Okay, we see it.
Can you see the screen?
Yes, perfect. You can go.
Okay. Good afternoon, everyone. I'm Emmanuel Vincent. I'm working as a senior researcher in electrolysis technologies in Tecnalia in Spain, San Sebastian, Spain. This is the beautiful view of the San Sebastian in Spain. So today I'm going to just briefly update about the anion exchange membrane electrolysis technologies and the current status and challenges of the anion exchange membrane fuel cells. Okay. So first a bit about Tecnalia. Tecnalia is one of the vast research and development organization. So there are many different areas of research and development R&D activities we do. So specifically here we do the hydrogen technologies activities, specifically low temperature electrolysis such as alkaline electrolysis, PEM electrolysis, AEM electrolysis, and photoelectrolysis. We generally focusing on the components such as membrane and electrodes and flow fields. So basically I would like to skip this slides. Okay, so there are many fuel cells. The fuel cell classified based on the electrolyte is used in the fuel cells. So most famous fuel cells are solid oxide fuel cell, alkaline fuel cell, and PEM fuel cells. In PEM and alkaline fuel cells are well-developed fuel cells, but the performance of the PEM fuel cell is quite good. It's the current density is quite good compared to alkaline fuel cell, but it requires platinum catalysts. So the alternative is alkaline fuel cell, but it works, but works only low current density. So now the alkaline fuel cell already worked in many different working areas such as terrestrial applications and some specific marine application. But in order to bring into the commercial transport market, it has some own challenges such as carbon dioxide poisoning and the pH change and reduced operation and participation of the carbonates. So with this PEM fuel cell and alkaline fuel cell is combined together, it's called anion exchange membrane fuel cell. So it has both the advantages of the PEM fuel cell and alkaline fuel cell. Especially, it also borrows the zero gap structure from the PEM fuel cell and the electrolyte and ion electrolyte, which is called anion exchange membrane, also the structure. And from alkaline fuel cell, it borrows the low cost catalyst, especially the non-PGM catalyst. So we know the operation, the fuel cell operation here based on this electrochemical reaction, the electricity is produced. So here in anion exchange fuel cell, the main significance is the ion, the hydroxyl ion, it moves from the cathode to anode. So based on this ion movement, the electricity is produced. So many research organizations and institutes are interested in this anion exchange membrane fuel cell because of the advantage of the combination of the both PEM and alkaline fuel cell. So this is it's all started almost 12 years before, from 2008 to 2020. So significantly the number of papers published in this research has been increased. And because it's also a developing technology. It's not well developed technologies like such as PEM fuel cell and alkaline fuel cell. So the research work is continually going on. Let's see how is the progress of this fuel cell technology. So mainly, this is the approach. We synthesize the novel polymer material for the membrane, and also we fabricate the electrode, the non-PGM electrode, then finally characterize both the membrane and the electrodes based on the ionic conductivity and stability are the crucial point of this membrane, and the electrode, its activity and the stability in alkaline conditions. So once it characterizes, it tested in the fuel cell testing station and optimized, then finally it's go for the diagnosis. Then once we have the results, very good results, then it's go for the modeling and simulation to predict the results. So the most important part of the anion exchange membrane fuel cell is the anion exchange membrane itself. Okay, mainly this anion exchange membranes decide the deciding factor whether it's go to the further or no. So main properties is the highly ion conductivity, the OH ion conductivity, and the chemical stability in this alkaline condition. The membrane has two different parts. One is polymer backbone and cationic, the functional groups. The polymer backbone, these are the common polymer backbone, and these are the common functional groups which are fixed in the polymer backbone. So once it is fixed in the polymer backbone, so it helps to conduct the ions, especially the hydroxyl ion, from the one side to another side. So this is the structure of the polymeric anion exchange membrane. Mainly, most of these functional groups are quaternary ammonium salts. So with this, the fuel cell performance depends on many different factors, such as electrode, catalyst used in the fuel cell, and the membrane and the polymer and operating condition. There are many different factors which decides the performance of the fuel cell. But in this particular So in this particular case, this is the maximum performance was found by the anion exchange membrane fuel cell at this. It's around 2.58 watt centimeter square at 80 degrees Celsius. So, but still it is improving, and most of the fuel cell performance are slower than this. This membranes with the alkyl terephenyl piperidinium membranes, they are showing very good performance in both the cases, whether it is in fuel cell as well as the electrolysis. In both the cases, it's showing very good performance, and also the specific power of the AMCFC, specific power of the AMC is 7.1 to 8.1 watt per milligram. So mainly this is working in the range of 2.58 it is reached. So this is the one of the big breakthrough in this anion exchange membrane fuel cell. Stability is the one of the major issue in the anion exchange membrane fuel cell compared to its performance, because most of the anion exchange membranes in the fuel cell condition, it's work less than 500 hours. After 100 hours, it started to degrade generally because of the nucleophilic substitution reaction and Hoffman elimination reaction. And some people, they manage to kind of find the stability for until 2000 hours with a very good performance. So this is the stability is the most important factor because it's degraded based on this nucleophilic substitution reaction and Hoffman elimination reaction and yield formation. So this hydroxyl ions are attack the polymer backbone as well as the functional group. So because of this attack, there is a degradation of the membrane and loss of the ionic groups in the membrane. So finally, it leads to the increase the over potential of the fuel cell. Apart from this anion exchange membrane problem, there is another problem with the normal fluiding and drying of the membrane, which also increases the over potential of the fuel cell. Okay. So on the other hand, there is another problem with the electrode, because electrode in platinum electrode, it's giving the lower over potential. But when we come with the other non-PGM electrodes, there is a problem with the non-availability of reactive OH sites in the interface surface of the membrane and electrode and the bulk solution. So it is also one of the other challenging we are currently facing in the AEM fuel cell. So although we have some problems and challenges, but still we are trying to improve as much as possible. So this is the Department of Energy from United States. They set up the milestone to improve the fuel cell technology to the until 2030. So first it start with, now this is the present stage. We are now in 0.65 at 1.1 ampere per centimeter square. So in later game, we would like to increase the catalyst durability, and first we start with 1 watt per centimeter square at the non-PGM level. Then finally our ultimate aim was to produce 1 watt per centimeter.
I think we lost Emmanuel due to battery reasons. So we cannot blame fuel cells. We have to blame lithium-ion batteries. I would just propose we keep 2 minutes to give Emmanuel the chance to reconnect. In the meantime, if you have questions on AEM, and not only lithium-ion batteries, feel free to put them in the Q&A.
Yes.
You
sorry.
are back.
Yes, I am. Yes. Thank you.
Go ahead.
Yes. So our ultimate aim was the one to increase this performance up to 1 watt per centimeter square at the PGM free membrane electrode assembly. Okay. So this is our current priorities to work on this AEM fuel cell to increase the performance and efficiency and understand the degradation mechanism, and to improve the membrane electrode assembly components such as catalyst, ionomer, and membrane, and reduce the critical raw material, because most of the catalyst is used nickel based. So we would like to reduce the nickel based catalyst to find alternative options. Still it is in the lower scale, so we need to build up in the higher scale. Also the fluiding and drying out must be prevented to development of the efficient water management strategies inside the fuel cell, and systematic deterioration due to the carbonate accumulation of the cathode must be alleviated, and efficient catalyst, and this can secure the economical feasibility and must be developed. So based on these priorities and based on this current situation, we have some recommendation to improve this AEM fuel cell technology, but mainly we focus on the membrane, because membrane and the catalyst, it has more major portion for the performance. So one is we need to find a very, very good membrane with the different polymers and annexional groups to find the optimal water with the optimal water uptake and gas diffusion layers and control structure with the hydrophobicity. And the second one is improved cell design and dynamic control for the operating condition. Also to solve the problems with the carbonate poisoning, water management, and heat rejection. And also this can be done when we study the detailed study of the adsorption of the quaternary ammonium cation head groups and the other side chain moieties. So with conclusion, we need to look for always the less expensive non-PGM catalyst with the different materials and fabric and electrode fabrication, and also other option to use the in the cathode feed instead of pure oxygen, and to find the alkaline feed direct alcohol and hydrogen anode. Okay, thank you.
Thank you, Emmanuel. On my side, I just have one question. I do not see questions in the Q&A, but one question about PGM. So the international target is to say PGM free by 2030.
Yes.
How feasible do you think it is?
Yeah, because right now the research are undergoing on mainly the alloys, like with the nickel ferrous alloys, they are showing very good performances, especially some of with nickel alloy and molybdenum oxide, and with the lead, it's showing very good performance. So within this time frame it is possible, but we cannot say completely possible, but we can say at least a very good improvement of this process.
So you are positive?
Yes, we are quite positive, because there are a lot of possibility. We are working hard to improve the performance in the molecular level with the DFT studies and dynamic model simulation. So it is positive, and I hope in 2030 it is possible to have a very good non-PGM catalyst for the both alkaline water, AEM water electrolysis, as well as the water fuel cells.
Okay, so in 7 years, we will talk again. I think there's a question from Simon.
Yeah.
Yeah, thank you very much for the talk. Very nice presentation. I mean, from my perspective, the membranes and the stability of the polymer is the biggest inhibitor for the introduction. And I would still say we are pretty far away from stable materials, aren't we?
Yes, Simon, but now I agree with you, because most of this membrane very less stable in alkaline condition because of due to this nucleophilic attack and Hoffman elimination. But recently there were many paper reported this is mainly due to the ether part of the ether components present in the polymer. So if we remove the ether component, then there is a possibility to improve the stability. But one problem, when we take out the ether, then there is a mechanical stability, low mechanical stability. But the chemical degradation such as this process can be avoided. So we are now, there were some membrane from Orion polymer, you might have known Orion, but they remove the aryl the ether, but the performance is good, but the mechanical stability is slow. So we are now trying to improve the mechanical stability and remove the ether. So there is one current possibility we have now to improve the stability of the AEM.
Okay.
Thank you, Emmanuel. There's a lot of polymer innovation going on. So there's a question from Solveig. Are you planning to synthesize your polymers and produce membranes at Tecnalia?
Actually, we are working on two different kind of polymers. One is PBA-based polymer, polybenzyl imidazole, and another one is because recently there is a paper report from Japanese scientists, but it is involving fluoropolymers. So when we have some fluoropolymer, the stability is high. So we are focusing on this too. But in Europe, as I know, the fluoropolymers are they are trying to reduce the fluorine content in the polymer, but we work in both different ways. One is PBA membrane and another one is fluoropolymer. So once we achieve very good level of the stability in the polymer, then we will look for the alternative to remove the fluorine into the very substrate solution. So we are doing synthesis the polymers, and first monomer, then polymer, then membrane ion exchange, then after ion exchange is the fabrication, then finally we put it in the fuel cell. So as the question answer is yes, we are working on that in technology.
Okay, so you need a lot of organic chemists.
Yeah, we have, but we also collaborate with the different parts of the European Union, especially for the synthesis of polymer, and the local universities for this.
Okay, thank you so much, Emmanuel, for the overview. And now I will give the floor to Marcel for a short wrap-up and conclusion on what we have heard this morning. Thank you so much to everyone for the very nice presentations, and I give the floor to you, Marcel.
Thanks, Fabrice. First, sincere thanks to all the speakers for their really inspiring insights in the different technologies. I took a few notes and I will try to make a short summary. From Stuart Jones, we heard that PEM fuel cells are still taking the main share in a growing but still rather limited market. We heard that the hydrogen cost is needed to be at $2 to $5 per kilogram for a wider spread of the technology in transportation. So there is still a lot of work to be done on the production side. Julie Mougin introduced us in the solid oxide fuel cells in a very clear and rich presentation. She highlighted the potential high efficiency of this system, up to 90% with heat recovery. The positive and the negative side of the technology. Positive side being, for instance, no noble catalysts are used. Different generations are in development for solid oxide fuel cells, with quite a lot of material developments and challenges in the focus, and the focus being really on lower degradation rate and durability higher than 10 years. Recyclability has been discussed for solid oxide fuel cells, and that needs still a lot of additional work for recovering the strontium and the yttrium as critical raw materials. Vincent Minier from Solvay gave us a nice overview of their rich portfolio on materials, ionomers, fluorinated ones, for various hydrogen applications. They are looking at alternatives to fluorinated polymers, and that is a nice thing for the future. From Michael Diederik, we heard that there is a potential complementary work between the EMIRI working groups and the activities of Hydrogen Europe and the Clean Hydrogen Partnership. There is a potential for collaboration in roadmaps 10 and roadmaps 15, with a specific focus on heavy-duty applications, and large fundings are available. Duplication has to be avoided as much as possible. From Simon Thiele, we heard that PEM fuel cells are confronted with a few challenges still. Membrane degradation has to be as low as possible, and they are working on improving the mechanical stability and the chemical stability of the membrane, at the same time making them as thin as possible. Focus is on novel materials for the membrane, but Nafion still being the king of the system. On the catalyst side, lots of work on platinum alloy catalysts as a main direction to reduce the platinum concentration and loadings. But there is still a lot of work to be done on platinum-free systems. Platinum-free systems are still far away. Maintaining the same performance with those systems will be rather difficult. On anion exchange systems, good presentation from Emmanuel Vincent, and the system is a nice wedding between PEM and alkaline fuel cells. I believe that the morning session was a very good introduction to what EMIRI is going to do in the afternoon. Further work on development of advanced materials and their KPIs, and that related to catalysts, related to energy efficiency, to degradation and new membrane developments. So thanks again for all the speakers in the morning, and looking forward to the discussions in the afternoon with the EMIRI members.
Well, thank you so much, Marcel. It's a very, very good summary and a good bridge towards the afternoon session. So we will resume at 1:30. You should have received another link for the afternoon session. So do some archaeology in your inbox. If you are not finding the link, you should have received it. And we will talk again in about 1 hour. See you soon.
Thank you.